Welcome back. Let's try question 3 of paper 2 IB 2024. A fixed quantity of 4.5 into 10 to the minus 3 mole of air is compressed at a constant temperature. Constant temperature means it's an isothermal process. The graph shows the variation of pressure P with volume V of the air. So here we are given a plot, and as the volume increases, the pressure begins to fall. It's an isothermal expansion. If you expand a gas that's at a constant temperature, its pressure decreases. That's exactly shown by this process. Suggest whether the air behaves as an ideal gas during this change. What is an ideal gas? An ideal gas is a gas that obeys the ideal gas equation PV equals nRT. Alright, now since temperature is constant, the entire right hand side is a constant, meaning for isothermal processes the product of PV must always be a constant. Let's check that out in the plot we are given. So let's choose a point. Let's go with this point over here and compute the product of PV. That turns out to be 4 into 10 to the 5, that's the pressure, and the volume is 3 times 10 to the minus 5. So this product is 12 Pascal meter cubed. Let's choose another point. This one is good, and its pressure is 1 times 10 to the 5 and its volume is 12 times 10 to the minus 5. So the product is 1 times 10 to the 5 P times V is 12 times 10 to the minus 5, which turns out to be again 12 Pascal meter cube. Now we see that pressure initially P1 V1 is equal to P2 V2. That's exactly the condition for an ideal gas, that the product PV must stay constant. Since that is obeyed by this gas, it is an ideal gas. The next question says that calculate the temperature of the air. Okay, so we can use this equation, PV equals nRT, PV know, we can figure out from the plot. We can also plug in V. The number of moles are given. We know the ideal gas constant and we can compute the temperature. Rearranging this equation, we have T equals PV over nR. Since we've already figured out that the product of PV is 12, I'm going to plug it in here. 12 divided by the number of moles. The number of moles are 4.5 into 10 to the minus 3. So I'll plug it here. 4.5 into 10 to the minus 3, and we use the ideal gas constant, which is 8.31. Time to put this into a calculator and see what we have. Let me do this for you. This turns out to be 320.898. But how many significant figures do we need? Since we are only given 2 as the input, we are going to curtail our answer to 2 significant digits. So this turns out to be 320 Kelvin. This only has 2 significant figures in it. That's great. Let's move on to the next problem. Outline how the kinetic theory of gases relates observable properties of a gas to the motion of the molecules. In other words, the question says, well, we can model a gas as tiny hard spheres moving around here and there in random motion. How does that motion give rise to temperature and pressure? So the question is that we need to explain how the motion of gas particles gives rise to pressure and temperature. Let's take the first link. Well, pressure, how do we define pressure? Pressure is defined as force per unit area. So if we take a vessel and we take a unit area, the pressure on that particular area is simply due to the atoms or the particles of the gas hitting against it. There's a force that those particles exert when they hit against the wall. So pressure is a direct consequence of the force exerted by the gas particles that are hitting against the container. Alright, and what about the other link? How is motion of the particles related with the temperature? If you look into your data sheet, you'll see an equation that goes as energy equals average kinetic energy of a molecule of a gas is 3/2 Boltzmann's constant times temperature. This is important because it gives us a direct relationship between the energy, the kinetic energy of a gas particle with temperature. In fact, the kinetic energy of a particle is directly proportional to the temperature. This therefore relates the motion, because motion is what creates kinetic energy. Kinetic energy is just half mv square. Is directly related with the motion of the particle. So this motion is directly linked with the temperature. If the particles begin to move around with a faster velocity, the higher speed, the temperature of the gas increases. So that's how kinetic theory of gases relates the motion with pressure and with temperature. Alright, I'll see you in the next video where we will take up the next question.